it still is, and so a very enlightening conference, so thank you very much for overview. So what I would like to talk about, a submetry, so it will be, I would like to advertise the subject. So it's, I think it's something very elementary, but there are questions which appear interesting to me and which are related to many different topics, to topology, analysis, geometry, Riemannian geometry. So, okay, so let me start. So what is a submetry? You can see what a submetry is from 2 points of view. So the one point, that is the definition which was made by Berezovsky, I don't know, maybe a few decades ago. So it's a special map between metric spaces. It's a map which preserves balls, which sends balls to balls of the same radius. So if it were injective, it would be an isometry, but so it's, yeah. You think of it as a kind of, surjection in the Lipschitz, in the one Lipschitz category. Like that. So this is one way to think about it. So the other way is to think just of one metric space X, and you consider a decomposition of the metric space in subsets which are pairwise equidistant. Equidistant means that so when you measure, so when you go along one subset and measure the distance to the other, it does not depend on the point. So typical something like this. So this is one set, this is another set. At each point, the distance is the same. Yeah. So, and if you have a decomposition of, so you can think of a submetry as decomposition of one given metric space, your favorite one, into equidistant and the closed equidistant subsets. What is the correspondence of these two definitions? So this is very simple. So if you have such a submetry, then the fibers are equidistant. And on the other hand, if you have such a decomposition, you just take the space of these sets and define the metric just to be, so this is one point, this is another point, and distance is just the distance between two subsets. So, okay, so that's what a submetry is.
Do you mean for every R or is it enough?
For every R. So you can localize the notion, so you can say that around each point you have some R such that, but so I want to have a global notion. And so you can do it for closed balls, for open balls. It's usually, it does not matter. So if you think you are improper, so your spaces are proper, then it doesn't matter at all. Okay. So examples. So the basic examples. So for the first type of submetries, I mean, so this is the same, but so the both types of submetries are the same objects, but say you can think of a submetry as a map or as a decomposition. So the first type, so there are maps which you which you have seen quite a lot of times, and which are submetries and where the submetries actually come from. So the basic map is the Riemannian submersion between two complete Riemannian manifolds. This is a submetry. A special case is a Riemannian covering map, but also an orbe covering between Riemannian orbifolds. And a very general, so for general metric space, just a projection onto one factor is a submetry. Okay, for examples of the other types, so the main example is the following. So you have an isometric group action on a metric space, and you consider the decomposition of the space into orbits. Then the orbits are pairwise equidistant, and then the space Y is just the space of orbits, so the quotient space. Then, so the second example is, so if you have a submanifold N, a smooth submanifold, and then you consider your space as a, okay, so this is, so your space is a tubular neighborhood for some epsilon which is smaller than the normal injectivity radius, and then you decompose this neighborhood in, in distance spheres. So it's clear. And now if you know what Riemannian foliations are, then these are essentially foliations which are locally equidistant. And then they are also globally equidistant, and they are closures. So if you take the closures of the leaves, then they define such a submetry. Okay, so these are the basic examples. So I think the ones you should have in mind are Riemannian submersions and quotient maps for isometric group actions. Okay. Some non-smooth examples. So the first one is more or less smooth. So you start with the convex subset of R2. It just should not be full dimensional, and then you decompose the whole plane into distance spheres from this interval. Then, so then almost all fibers are almost smooth, so they are C11, but not C2, and there's one fiber which is just a convex subset. So this one is more or less, you can think of it as a smooth, but if you just take a more general convex set, then you consider it as a smooth one. So the next example might be a bit more disturbing. So you cannot construct, or at least I don't know how to do it, so how to construct such a bad example in the Euclidean space. But if you are in the hyperbolic space, then you can do the following. So the picture will appear soon. So you can replace these convexity assumptions, but just by the assumption that you are not too curved. So you should not be more curved than the horospheres. And then the distance function to such a subset will be still a submetry. And what you can do, for instance, such a set. So it does not have to be equidimensional, so you can do something like that. So just these curves should not be less curved than the horospheres, or they can just be parts of the horospheres. And then you take the distance sets to this subset. Then again, the other distance spheres will be more or less smooth, but this one is bad. And in high dimensions, you can make this guy even much worse. So, and a similar one is the so-called tennis ball submetry. So you can sit in the unit sphere and take the half of a great circle and consider the distance functions to it. So then, so the pictures are by Marco. So the first picture, these are the distance spheres around that one, and the last submetry is given by the. So what you see are the fibers of the submetry. So you see two special fibers. This is this half circle and this half circle, and the other ones are in between. And so this is a picture you might have seen on a tennis ball. Okay, so these are the kind of non-smooth examples one should have in mind. Okay. And then there is yet maybe a last class of examples. So this is where maybe the interest in these guys come from. So these are the so-called isoparametric hypersurfaces in the Euclidean spheres. So what are these guys? There are three equivalent formulations, but the classical one is the following. So you call a hypersurface in the sphere, you call it isoparametric if the second fundamental form has the same eigenvalues at all points. So you don't have to find it interesting. No, but this is so equivalent. So from point of submetries, equivalent condition to that is just that the parallel subsets to this the hypersurface, they define a submetry. Or another equivalent statement is that the focal points, if you start there, they come at the same distance, independent of where you start. And so these guys, though, they were studied for over a century, and by many people. So again, because they are complicated enough, so they are easy enough so to start working with them, but they are complicated enough so that it's very difficult to classify them, and they lead to a very interesting algebraic topological problems. So I think so they are essentially classified, but it has been very long, a very long way. Okay, so what? It's a very easy definition. So what are the basic questions? So I consider, so how bad can the submetries be? So how many of them are there? So are there worse things than that? Can one classify submetries in model spaces, or model spaces? So really the Euclidean space. So the Euclidean space of the Euclidean sphere. How can you decompose the Euclidean sphere in equidistant subsets? It's a very naive and interesting question. And then, can one, so some regularity questions. So why is it the case so that in the hyperbolic space it is much easier to find non-smooth examples than in the Euclidean case or in the sphere? Okay. So, these are the basic questions. Now I would discuss some answers to them. So the first is a very basic structure. So from now on, I essentially, so I prefer to think of submetries in the second way. So I have my good space, so a smooth Riemannian manifold. And I would like to say something about possible decompositions in equidistant subsets. So I also should say so that submetries, so they are certainly, so these are very special objects. So if you take a random Riemannian manifold, compact one, there will not be any submetries. There will be some local ones, but even local ones will only exist, only submetries to intervals. So there will be no more complicated decompositions of your manifold. So this is, so submetries exists only in special situations, but on the other hand, so if they sometimes appear naturally in some questions related to rigidity. So one famous example is, so there is a classical theorem, I don't know by whom, so that if you have a Riemannian manifold with sectional curvature at least 1, so now if the diameter is larger than pi over 2, it's a theorem of Grove-Schurhammer, then the Riemannian manifold is a sphere, topologically. Now, if you go to the boundary case, and if you ask about, so what are Riemannian manifolds, such that the curvature is at least 1, but the diameter is at most pi over 2. And then it turns out so that either it's topologically a sphere, or if it is not, then you find a submetry of the space, and then you prove finally that your space is a projective space, either CPN or HPN or RPN or OP2. So this was a famous result of Grove, Gromol, and then Wilking. Okay, so now coming back to the basic structure of submetries. So this result, okay, so assume we have a complete Riemannian manifold and we consider an equidistant decomposition and would like to understand something about the quotient. Then there are the following easy statements. So first of all, because so the condition of being a submetry is stated in very simple metric terms, it is stable under all kind of metric operations. So it's stable under convergence. So if you have a submetry, if you have a sequence of submetries, you go to a Grommer-Hausdorff limit at a submetry. If you blow up a submetry, it stays a submetry, and so on. Okay, so now submetry is a one Lipschitz map, so it sends curves to, it does not increase the length of curve, but as for Riemannian submersions, there are special curves, so the horizontal ones, which run orthogonal to the fibers, and the submetry preserves their length. And in fact, so if you have any curve below, you can lift it to a curve with the same length, static at a given starting point. So there are a lot of horizontal curves. What the base preserves is, so what the base has automatically, so it is a geodesic space, so if you have any 2 points, then you can connect them by geodesic if it's the same upstairs. So if you just have a point, so one point is that, the other point is that, if you pick one point in this fiber connected by a shortest geodesic to the other fiber, then this projects to the geodesic downstairs.
But these horizontal lifts, are they unique?
They are not unique. They are not unique. They are extremely non-unique. Okay, and the space, so the quotient is usually not a manifold, but it preserves the lower curvature bound. This is the metric analog of the O'Neill formula. So if you have Riemannian submersion, then there is a formula which computes the curvature on the base, and its curvature of upstairs plus some tensor. Okay, so and then there is just an infinitesimal to local to global properties. So as Andrea asked, so there is no, so you can study local submetries, so which satisfy this condition for small balls. And you can also ask about infinitesimal ones, so these are the ones that if you blow up, you see a submetry, and it is all the same. So if you have a proper space and all blow-ups are submetries, then it's a submetry. Okay, so this is more or less element. So sectional curvature, yeah. Okay, so this is the a result obtained jointly with Vitaly Karpovich. So it tells something about the possible fibers and the possible base space. So what does it tell us about fibers? So it tells that the fibers have positive reach. What does mean positive reach? So it means that on a small neighborhood, there's some epsilon such that on an epsilon neighborhood of your subset, you have a unique projection, unique closest point. So equivalently, you can think of it like in the following way, so that if you start at any point, then so if you start horizontally, then you minimize the distance to your space for some time. So what is forbidden is something like that. So, and what is also forbidden is, say, a curve which has infinite curvature there. So this condition of having positive reach, you can think of it as having a second fundamental form defined in a weak sense, bounded from below. So it should not be too curved extrinsically. So this tells us that the fibers cannot be much worse than that. What does it tell us about the quotients? So in general, Alexandrov spaces can have a very complicated local structure. So you can think local geometric structure. So you can think of just any pretty wild boundary of a convex body. Then there are a lot of, so then at any point, the injectivity radius is 0. So there are some directions where you stop immediately to minimize the distance. Now here it is not the case, so the quotient essentially, so what we prove is that the quotient is a stratified space. So at each point you have some epsilon such that going in any direction you have, so you minimize the distance, so you really have a geodesic going there for some time, and all the strata are really Riemannian manifolds. And they have, so also on these Riemannian manifolds, the curvature is also bounded from above. Not uniformly, but it's bounded from above. So if you approach, so if you go on one stratum and approach a lower one, then the curvature usually explodes. Finally, the topology of the map is also, so it's, the topology of a submetry contains, you can think of it as so it's built from finitely many Riemannian submersions. Not quite, but more or less. I mean, so you have, so over each of these strata, the pre-image fibers, so is a fiber bundle. It can happen, so if the fibers are like that, then it's a fiber bundle, this fibers of this type. But this is kind of unusual. Okay, so if you have studied or if you have encountered, if you worked with transformation groups, so then this is the picture which you observe there. So if you have an isometric group, so a compact Lie group acting on a Riemannian manifold, then the quotient is like that, and this strata correspond to the isotropy, to the types of isotropy groups. Okay, so another statement, so this concerns the presence of such fibers. So first of all, so the first the following observation, so the following statements are equivalent. So all fibers, so if all fibers are topological manifolds, then they are C11 manifolds. So the C11 is some critical value. So you cannot do better. And this happens if geodesics which are normal to fibers stay normal for all times. So you can see it at this example. So here, if you start normally here, then you stay normal for all times. But if you start normally here, then you arrive at this special point, and there you are not, so beyond this point you are not horizontal anymore. So here, so in this direction you are horizontal, but there you are not. So you intersect these fibers not horizontally, not normally. Okay, and observation is so that if the quotient has empty boundary, meaning that there are no strata of codimension 1, then such fibers do not happen. Then all fibers are really manifolds without boundary. And this is a local, so this is a local statement. So in fact, all fibers, so all regular fibers, so all fibers sitting around the largest stratum at around and above all strata which are not in the boundary, they are manifolds. Okay. And again, so also this condition is stable, so transformality is stable. So this is probably the class which is the right generalization of isometric group action. So this, so submetries given similar to this are more, are stranger objects. So are there questions so far? So this is general structure. So now some more special statements. So the first, okay, so maybe before going further, so
Means that these geodesics are always normal to the
sorry.
transnormal
transnormal means that geodesics stay normal, and this is equivalent to the statement that they are, so that such fibers do not exist. Now the non-smoothness. So the non-smoothness is not only related to the presence of non-manifold points. So for instance, if you just take the hyperbolic plane H2 and take in this H2, so you start with the geodesic and then you continue with a horosphere. Or just take any curve whose second fundamental, so which is C11, and the second derivative is just bounded by 1. Then if you take the parallel curves to it, so these are not geodesics in H2, these are just the distance, so you go distance 1 in this way, and this is not a geodesic, but this gives you a decomposition of H2 in parallel submanifolds, all of them being C11 and not beta. This can be a bit surprising, so you start with something, so you have smoothest manifold there, and you have something which is defined in terms of the metric, and it is not smooth. Yeah? But, so it has some regularity, but not the best one you would expect. What can appear a bit surprising is that the strata, so the quotient space, it inherits the smoothness automatically. So that if the total manifold is smooth, so then the strata, they are smooth even if the fibers are, so somehow you would, one might think that if you have some non-smoothness, then this non-smoothness is separated somehow. So you have some non-smoothness in the fibers, non-smoothness in the base, and this non-smooth part, so they add up, so they cancel. So that you get the smoothness upstairs, but this is not the case. So the base is always smooth, and so maybe just one word about the proof of this fact. So we have here M, we have here N, and assume just forget about submetries. So this is a statement about Riemannian submersions. So you have a smooth manifold, and you have another, say, manifold with a metric which is not quite smooth, say C2, and you have a Riemannian submersion. Now, why is this metric downstairs smooth? Now, the point is the following. So if you pick a point upstairs, you pick the horizontal plane, and you exponentiate it. Then you know that this small exponential chart is mapped by diffeomorphism. So the projection is a diffeomorphism to an open subset here. Now, what you want to prove is that you can pull the metric back, and you want to say that the metric here is defined in a smooth way. Now, how is the metric, so how do you measure this new metric? You take a vector, a tangent here, and you project it horizontally. This is your new metric. So to project it horizontally is the same as to project it to the vertical part and subtract the projection to the vertical part. So you only need to say that the vertical spaces, so that if you go along horizontal geodesics, that your vertical spaces vary in a smooth way. So observe so there's no in the vertical, the vertical spaces in the vertical direction that vary in a very non-smooth way. But in the horizontal direction, you can express them just in terms of the second fundamental form at this one point and the Jacobi fields. So the non-smoothness of the submanifold, it is expressed in the very non-smooth dependence of the second fundamental form along this fiber, it surprisingly does not play a role. So what plays a role is just the smooth, so the Jacobi equation, so the curvature tensor upstairs and the second fundamental form just at this one point. So that's the proof of the first statement. To the second one, yeah, this is something, so the statement is in a picture, so if all regular fibers are C2, then something like this cannot happen. It's not so if you see this picture, it's not so surprising. I mean, so if you, so what it tells you, so that if you go, so if you take a fiber which is very close to a non-manifold fiber, then around this point you can find something like that, so that the curvature here is very large, and the curvature here is essentially the curvature here. So there is some point where yeah, the curvatures do not match the second fundamental forms. Okay. So now come maybe the difficult. Okay, yeah.
Does it mean that all fibers are C2 regular?
Then all fibers are C2 regular. Yeah. No, so if the regular fibers, so if the fibers, so you have the full dimensional fibers, so sitting over the regular part, so they are, so most fibers are, so most fibers are C11 manifolds always, and if they are C2, then no singular fibers. So then all fibers are C2. So, but more important is so that no fibers of this type exist. So all fibers are manifolds. So so you have a transnormal decomposition of your space. So now so this result is really so about curvature, and this is something, so this explains where this non-smoothness comes in. So actually, so this is one of another point. So I told you so that submetries appear often in some rigidity results. So another famous place where submetries appear is the following. So there is, so if you have a space of, if you have a Riemannian manifold with curvature larger than 0, so larger than at least 1, then it is compact. If it is larger than 0, then it tends to be compact. So if it is really larger than 0, then it is diffeomorphic to a point. So diffeomorphic to the Euclidean space. Yeah, it's homotopy equivalent to a point. Now, if you have a non-negatively curved space, which is non-compact, then it's a so-called Soule theorem of Chiga and Gromol, which tells you that there is a compact, totally geodesic submanifold such that your whole space is diffeomorphic to a normal bundle of this submanifold. So the whole space is a manifold, yeah. And here, so you have again, so two assumptions, so playing against each other. So you have non-negative curvature, so which makes your space compact, and you have non-compactness by assumption. So, and then it turns out that there is a submetry, so that there's a submetry of the whole space, a so-called Sharafudinov retraction from the whole manifold to the Soule. And this was constructed, so it's constructed by purely metric means. It was constructed by Perelman, and it was not clear if it is smooth. Just because the construction, it uses gradient flows of non-smooth functions, so there's no chance that you see it from construction. And so it was a question for a long time if it is C infinity, and it was proven by Wilking at some point. And so this is this fits. So this is closely related to this stuff. So okay. So now in non-negatively curved spaces, the following happens. So the statement is the following. So if your manifold is non-negatively curved, and all fibers are C0 manifolds, then you are essentially smooth. So you are always C2, and all fibers are C infinity up to possibly, yeah, a small set. So at least it is C infinity on an open dense subset. Okay, so just one word about the proof. So what does the non-negative curvature has to do with smoothness, and so how it prevents this kind of examples. Okay, so what happens here? So why this example is possible? So you just take parallel sets and you don't get problems. Why does not the same happen in the Euclidean space? Now, in the Euclidean space, as soon as you are a little bit curved, you cannot take parallel sets. At some point, you get a focal point. So as long as you don't have focal points, you have much more freedom. Now, as soon as you are non-negatively curved, then if you have a submanifold, then either you have focal points or you have some rigidity, or you are really flat orthogonal to it. Now, how is smoothness really related to it? So how can you deduce it from the assumptions? What time did I start?
45.
Okay, so I still have some minutes. Good. Okay, so how do you prove that? Okay, so let us. So the basic observation is the following. So if you have a Riemannian submersion and you have a fiber which projects to a point, then if you go horizontal, so if you start in this point and you consider the horizontal lifts of this geodesic, then you see a conjugate point downstairs exactly when you see a focal points upstairs, saying that in these directions the focal points come at the same time. Now assume that you are on a, say, on a, if you are in the Euclidean space, so assume that your total space is the Euclidean space, and you have a hypersurface. Then for a hypersurface, and you have a Riemannian submersion. Then this observation would tell you that in the normal direction, all focal points come at the same time. But the focal points in the Euclidean space, the distance to the focal points is just the same as the corresponding eigenvalue of the second fundamental form. So if you are equifocal in all directions, so then it means that your second fundamental form has constant eigenvalues. So it tells you that your hypersurface is a surface of constant mean curvature. Now this is the case for the hypersurfaces. You can do the same for submanifolds in lower dimension, and for and the main point is again so that you have enough focal points. So that the focal points control the whole second fundamental form. Now, in a general case, so if your manifold is not the Euclidean space, then the relation between the distance to the focal point and the second fundamental form is much more complicated, so you cannot express it, but the basic idea is the same. So that you use this equifocality, then you make some strange bootstrap argument. So that's all I think what I want to say about this smoothness statement, and then I would like to say a little bit about algebraicity, which I find maybe the most surprising part. Locally, so if you have a submetry and you sit in a point, you blow up, then you see a submetry of Euclidean space. And this has some vertical parts, which is tangent to the fiber, which is not important. And then if you restrict to the horizontal part, you see the essential part of your of an infinitesimal portion of your submetry, which also models locally your submetry to a large extent. So in order to understand, so if you want to understand all submetries, it's maybe natural to understand the submetries of the Euclidean space first. Okay, so and this submetries of the Euclidean space, so if you blow up and take the essential part, then it has 0 as a fiber. So it's the same as to say that they are homogeneous. So if you restrict the vector, then so if you multiply the vector by some constant, then yeah, it's multiple. So that so the submetry is a cone map. Or the same is to say that you can consider the submetry as a submetry on the unit sphere, and then you just cone it off. And now, so there is this. Okay, so we. So here's the statement. So if you have such a submetry, then it is algebraic. So first of all, every fiber is an algebraic submanifold. So that it is analytic, so it's not so surprising. So once you know that you can say something special about the mean curvature vector. But so algebraicity may come, is surprising. So and then what is even more interesting? So you can consider the algebra. So you consider the space of all functions which are constant on all fibers. So I mean So you call a function basic if it is if the restriction to any fiber is constant. And you consider the space of all such functions. The statement is this space of functions contains a lot of polynomials, and this algebra which you get is polynomial, and it determines your submetry. So if you have this algebra, so it has enough polynomials to distinguish all spaces. So the proof is not very surprising. If you just start with any function, and you want to obtain a function which is constant on the fiber. So you would like, so what you do is you take the mean of this function along the fibers. The point is so that the fibers are of different dimensions. Usually, if you take this mean, so you take the mean on any fiber with respect to the volume of the fiber. So now it's clear that this is reasonable in the L2 sense, but it's not clear at all that it preserves some kind of smoothness. And that's somehow the main. Once you know that it maps smooth functions to smooth functions, then it's somehow clear because just by rescaling it will send polynomials to polynomials. But the smoothness, this is related to some, really to some, not very deep, but to some analysis. Okay, so and once you are here, you can start asking questions about this algebra. So what is this algebra? This algebra is in the classical situation. So if you have a group, so if you have group acting on the unit sphere, this is just a representation of a compact Lie group, then this algebra of basic polynomials are just the algebra of invariant polynomials. So what we have recovered here is the same object without that a group is present. And now you can start investigating the algebraic side of this. So this algebra of invariant polynomials, and try to find connections between the geometric, topological, and algebraic side. So this was done by, this is done, so this is ongoing work by Ricardo and Ende. So first of all, one can, in a very easy way, describe what these possible algebras are, which you obtain in this way. So namely, an algebra of polynomials. So if you take an algebra of polynomials, then it will come from a submetry if and only if it is invariant under the Laplacian. So it's a very easy condition. So you consider algebras. So subalgebra of the polynomial algebra which is invariant under the Laplacian. That's automatically turns out it's finely generated and has much more properties. And the fibers, so the common. So if you take the set of points on which every polynomial, so every element of this algebra is constant, then this gives you a decomposition of your Euclidean space as a submetry. And all submetries are of this type. So it's kind of, I think this is a very surprising result. And then one can start developing, so writing a dictionary. What are the algebraic properties of this algebra of polynomials, and to which properties of on the topological side they do correspond. So for instance, the transcendence degree of this algebra is the dimension of the quotient, something like this. So this is the very basic one. But there are much deeper statements. So for instance, one can analyze the Laplacian of basic functions, so which is more or less the Laplacian downstairs, and there are eigenvalues, and then there is also a Weil's law, and so one can, first of all, one can prove that there is this Weil's law, and then the coefficients which appear there, they can be read off in these generators of the algebra. So it's some funny things. Okay, and so this is about the algebraic side, and now I would like a last statement about the topological, a topological result, the following, which I would like to present. This algebraic part and this so I think this topological statement is probably the easiest case of some much more difficult statement, much more general one, which I don't know how to prove. Okay, so the statement is the following. So if you bound the geometry, then there are only finitely many submetries of your space up to foliated homomorphisms. So so in codimension 1, so what are these objects? So if the fundamental, so if we would not assume that the fundamental group is finite, then the quotient space, this Y, could be either a circle or an interval. So if it would be a circle, then such a submetry would really be Riemannian submersion onto a circle. So here we assume that the fundamental group is finite, so the quotient is just an interval, and the decomposition of our manifold, it has two special fibers, and all other fibers are regular. So if you take here the middle fiber, then it divides the submanifold into two parts. Each part is a disk bundle over this singular. So this part is a disk bundle over this singular fiber. This part is a disk bundle over this singular fiber. So the whole thing is, the whole manifold is the union of two disk bundles glued along the sphere bundle. So, and the statement is so that there are only finitely many of such guys if there is some geometry bound just on the total space, so not on the objects. Okay, so and maybe I just say 2 words about the proof. So the first observation is one should, okay, so the first observation is if we use the theorem of, what is it, Cheeger-Gromov, so that the space of such M's is of differomorphic classes is finite, and if you have a sequence, then they converge. So we can assume more or less so that we are on the same manifolds and just the metric change a little bit, and we have different decompositions. So now you can what you need to say first is that you have no collapse. How is this prevented? Since you are simply connected, so these fibers, they are real, so you observe that they have lower dimension, and this means that whenever you start here horizontally, whenever you come to this fiber, you find a focal point. Now, if you go here normally on a geodesic, then its image downstairs, it makes thus. So so if this distance is epsilon, then every epsilon you meet a focal point. So this would mean that you have, so if this is too short, this would mean that you have too many focal points. This is impossible, since you have bounded curvature. So now, once you have fixed that these submanifolds are okay, so that this is large enough, then you know that the second fundamental forms of this and of that are bounded, and so you can also make these fibers converge to the limit space. But then you still need to do something to prove that the gluing maps that they define the same, that they are isotopic to each other. So that's more or less the proof. Okay, so I think that's all I wanted to say. Thank you very much for your attention.